Look into the bowl of a highly polished spoon. Even though the metal is smooth, your reflection appears completely upside down. Flip it over to the bulging backside, and you return to being right side up, though your face is now shrunken and distorted. This is a deviation from a standard flat mirror, where the image matches your actual orientation and size. These changes in the image occur because a curved surface alters the angle of reflection for every ray of light that strikes it. We can model these surfaces as cross-sections cut from an imaginary sphere. A surface that curves inward, like the bowl of the spoon, is concave, while a surface that bulges outward is convex. Understanding why our reflection flips requires us to move past the object itself and map the geometry of light as it bounces off these specific spherical curves. To simplify the physics, we can represent the spoon as a two-dimensional curve on a mathematical grid. We define this curve using two landmarks: the pole, at the center of the mirror's surface, and the center of curvature, which marks the center of the sphere the mirror was cut from. The straight line connecting them is the principal axis. When parallel rays of light strike a concave mirror, the inward slope of the curve causes them all to reflect inward. These rays meet at a point exactly halfway between the pole and the center of curvature. This intersection is the principal focus. This focal point is the fixed geometric value that determines the position and size of any image the mirror produces. Predicting an image only requires us to track two specific rays of light coming from the same point on an object. The first ray travels parallel to the principal axis, and, upon hitting the mirror, always reflects directly through the principal focus. A second ray passing through the center of curvature hits the mirror along its normal, meaning it reflects straight back on its own path. The intersection point of these two reflected rays is where the image forms, in this case below the axis and upside down. A convex mirror forces parallel rays to diverge or scatter outward. However, if we trace these scattered rays backward, they appear to originate from a virtual focus located behind the mirror's surface. To turn these drawings into calculations, we use the new Cartesian sign convention, treating the mirror's pole as the origin on a coordinate grid. This chart shows the mirror formula. By measuring the distance of the object as u and the image as v, we find they share a consistent relationship with the focal length, f. Combined with the magnification equation, we can calculate the exact position and height of any reflection. This explains why the spoon's reflection flips. The orientation is determined by the object's distance relative to the mirror's specific focal length. Because these geometric rules are universal, they allow engineers to scale the physics of a spoon up to industrial levels. This Solon furnace uses a massive concave mirror array to capture parallel sunlight. By forcing that light to converge at a single massive focal point, the structure generates enough heat for industrial processing. We see the inverse application in this searchlight. By placing a high-intensity lamp at the focal point of a concave reflector, the mirror sends out a concentrated parallel beam of light that does not scatter over long distances. This side-view mirror uses a convex curve to intentionally shrink the image. This allows the driver to see a much wider area of the road behind them than a flat mirror would allow. By controlling the curvature of these surfaces, we can either concentrate energy onto a single point or project light in a narrow, controlled path. But these rules only apply when light bounces off a surface. What happens when light passes through a medium, like water, and begins to bend?